I'm Lisa Lippincott, and I'm here to talk about why loops end. Now, occasionally I give talks where my title is a little obscure. I don't think this one is. We write loops in our programs. We execute those loops. Sometimes the execution of the loop may come to an end. Sometimes there may be a reason why the execution comes to an end. I'm going to talk about those reasons. So, jumping right in, why loops end, reason number one, the heat death of the universe. So here's the deal. Computation, like so many other activities, increases the entropy of the universe. It converts free energy, which can do work, into thermal energy, which cannot. This process is irreversible. Any loop left unchecked will consume all the free energy in the universe to the point where not even a single instruction can be executed, and the loop will come to an end. So there's a reason. Let's try out that reason in the context of code review. Our interlocutor here asks us why a certain loop will end, or whether a certain loop will end. And we explain about the free energy. This does not please our reviewer. But if you ask the wrong question, sometimes you will get the wrong answer. So what could the reviewer ask to get a better answer? What more specific sort of reason might our reviewer be looking for? Might be looking for a non-cosmological reason. And that's actually a fairly vague and expansive term. So some problem with that, but so it does get to what the problem with the heat death of the universe as a reason is. It is big and far away, and we want a reason that is contained and close to us. We want a reason that's in our program. In fact, we would like to have a reason that's in part of the program near the loop. So, trying again, being much more specific, will this loop end for a reason that is expressed on every code path that enters the loop, is complete before any part of the loop is repeated, and is not separated from the loop by a function interface? So this is saying, yes, we want it in our code temporally before and nearby in some sense. But, so what's this function interface thing? So today I'm going to be working with a system for writing function interfaces into our code that looks like this. The function interface is essentially a block of code that sits in between the caller and the implementation of the function. And the part above the implementation line expresses preconditions, things that the caller is responsible for, and is executed before the implementation. The part below the line is executed after the implementation and expresses post-conditions, things that the implementation is responsible for. And we use function interfaces to divide our programs into neighborhoods so that we don't have to consider the entire span of our program all at once. We can say our neighborhood ends at the function interfaces, and we will consider one neighborhood at a time. And if we set it up right, of course, we can have the neighborhood completely contained in a translation unit. That's going to make things much easier on our analysis. So, having said that, you can come back here. We'll call that a local reason. A local reason is one that's before the loop, near the loop in the sense of function interfaces, and expressed in the code. So what do? We write a comment into the code. I don't care for that sort of reason. This is my prejudice. Comments can be misleading. It's very easy to be vague in a comment to express a reason that isn't clear enough. So I'm going to introduce a new reviewer, our robot pal. And here, our robot pal only reads the executable code. The interface is included, they're executable, but not the comments, not the things that are intended only for people. So this is our problem statement today. Explain why a loop ends in such careful detail in the structure of our code so that a robot can determine whether our argument is correct. And of course, by robot, I don't really mean robot, I mean algorithm. And by algorithm, I definitely do not mean one of these newfangled cat recognizers. I mean a good old-fashioned algorithm that we carefully design and we keep small and so that we can all understand it and standardize it so that we have an idea of what it means to have a very clear reason in the structure of our code. So that's what we'll be aiming for. Reasons that are good enough that a simple algorithm can understand. So what does our algorithm look for? I'm going to say there's three things. The first one is periods of stability. It looks for periods when the state of an object isn't changing. The second one is substitutability, moments when we know that two objects have the same value. And the last thing it looks for is repetition. Times when two operations, when one operation is so like a previous operation that it is going to give a similar result. So that's if I add two numbers and then I add the same values again, I get the same answer. So the robot is going to know these sorts of things. How will the robot know them? We're not going to build detailed knowledge of all the functions into our robot. Interfaces will tell the robot about these things. So this is what we're going to do. We're going to design function interfaces that can tell the robot about these things, and we will try to use that to show the robot that various loops end. So let's take a look at an actual function interface. Here is a somewhat paraphrased interface for the equality operator on integers. And I want to say, yeah, we need interfaces even for basic operations to make this work, because we're not going to teach the robot about how all the basic operations work. We'll just teach it how to read interfaces. And here, we're going to say extend stability for A and B. That is, the caller is responsible of this operation is responsible for holding A and B stable. They will have the same state throughout the operation. And when we're done, we're going to transfer the stability of the result. The caller gets a new thing that it knows is stable, which is this result object that didn't exist before. So that's how stability works in interfaces. We also have discern, which is about repetition. Here we say, if A or B has a different value, that is a different call to equal. And if they have the same values, then okay, that's a repetition of a previous call. And the thing we get out of repetition is that if it is a repetition of a previous call, then the result will have the same value. And that's why we discern the result in the epilogue here. And finally, we get a bit of substitutability in this interface. Here, if the result is true, we're going to say A and B have the same value. That's substitutability. And that's all the pieces of reading an interface. But it's not all the things we want to put into the interface. I'm going to stop for a second and say, this business where we put a branch in the interface always bugs me a little, because it means that anybody who is using this function actually has one of two different post conditions. depending on how the branch goes. They don't really know what their full post condition is unless they repeat the branch. They repeat the branch, they know on this branch, it goes one way, it's substitutable. On that branch, that direction, it's not. Don't like doing that because it complicates the robot's job. Complicates people's job too. We don't want to put a lot of branches in interfaces because then there are a lot of paths to examine. But I'm going to make an exception for comparison operators. I'm going to say it's okay to put one in there because honestly, how often do you call a comparison operator and not branch on the result? So I'll allow that one. But if we are allowing that, I'm going to take advantage of it. I'm going to squeeze all sorts of stuff in here that is helpful facts that we know depending on which way this branch goes. And I'm going to stick in some helpful facts that know either way. So like if we compare something to itself, it's going to produce true. If we compare B versus A, it gives the same result as A versus B. So these are things that we can put in the interfaces. And if you're squinting a little bit because it looks like there's a recursion in there that would be unfortunate, there's a trick for getting around that. There's a long version of the talk online where I talk about getting around that recursion. But just live with it for the short version of the talk. So our interfaces will have these extra helpful things put into them. And I'm going to use my judgment about what helpful things are in there, but I'm going to try and say the most important things that we can say without branches. And in the case of comparisons, the most important things that we can say even with one branch on the result. So that's what goes into our interfaces. Let's look at a loop. This is the simplest loop I know. This loop ends. I am convinced. But have we convinced a robot? Let's ask. Yeah, the robot, I'm saying when I looked at what the robot sees, the robot can actually figure out that this loop ends. Why can it figure out this loop ends? Because it's looking at interfaces. There's only one interface here. False needs an interface. Any sort of literal has an interface. So here's an interface for false. We're going to treat it like a function that produces a value out of nothing. Just leave off the parentheses because literals don't work that way in C++. I think Lisp, maybe they do. It's some language they do. So here we are. False creates an object, tells the caller that it's stable. It creates an object with the same value every time. And there's this branch at the bottom of the epilogue. In the epilogue, it branches on the result of false and says, one side of that branch never happens. Does it really never happen? It doesn't really matter to us. It's not our fault if it happens, it's false's fault if it happens. If the branch goes that way, then something is wrong with the implementation of false. So we can look at this interface and say, our branch is repeating that branch. And we know which way that branch went if false is doing its job. So we know our loop exits. Like first time through, we see, oh, it's going to go in the false direction. We know what the false direction is. It exits. So there is a proof that a loop ends, just written into our code. And I've had people tell me that it is impossible to prove that a loop ends. They're not thinking of this loop, I think. We can prove that this loop ends. So let's make our problem just a little harder. How about this one? While 0 is not equal to 0. Apparently our robot approves of this loop. It can find a reason why it ends. And it's going to find it by looking in the interfaces. In particular, something that we really ought to put in the interface for not equal, for ints is that when you compare something to itself, it's going to return false. A thing is not equal to, a number is not equal to itself. And we know which way false goes, so our robot can read all of that stuff and figure out that, yeah, this loop's going to end just like the other one did on its first try. Let's make it a little harder. Okay, here we have an actual counting loop, but one that doesn't go very far. Here, the robot can see that we are in fact comparing 0 to 0 first time in, because it knows that 0 was made stable, or that I was made stable when we initialized it. And we have not given up our right to the stability of I. So it's still 0 when we do the comparison. And that other 0 gave us the same answer because 0 is one of those things like false that always gives us the same value. And so it can say, yeah, this one gonna exit before we even get to plus plus I. But make it one harder. So, counting from 0 to 1. Apparently, our robot can see how to do this. Why can it see how to do this? Well, it's gonna see the interface for increment. I mean, maybe it exits, it tries two different ways. If it exits, then we're done. If we go around the loop, we come to the increment. And during the increment, we say, oh, increment gives us the same value as adding 1. So that's the first line and the last line of this interface. The expected value is a plus 1. And down at the bottom, we see, yeah, a has reached its expected value. So post condition is that the new value is 1 more than the old value. So, okay, the robot can see the relationship between increment and addition because it's in the interface. But addition is going to tell us these handy facts because adding 0 is such an interesting common case that surely our interface is going to tell us that adding 0 gives us the same value back. So we counted to 1. Now, these chains of reasoning are getting a little more complicated. And maybe it's not obvious to a human reading that code who hasn't gone through all the interfaces why this is happening. So I'm going to start putting things in there, extra checks in there, that are really there to help us humans see what's going on. So this is an extra thing for the robot to check. It's going to say, oh, can you figure out that 1 is equal to 0 plus 1? And it's like, yeah, robot figured that out. And that will help us keep our place. Just putting in an extra thing to help us keep our place. So let's make this one harder. Honestly, when I got to this point, I thought the robot was going to not be able to figure this one out. And then I actually went through all the interfaces it's going to be using here. And it turns out there were enough clues that the robot could piece together because I hadn't considered going in how you would write the interface for 2. You have to write it as a template specialization because that's really the only way to get at the values of single-digit numbers. And if you're writing a full specialization anywhere, you might as well say that the most important thing about 2, which is it's 1 more than 1. So the robot can put that together and say, oh, 0 plus 1 plus 1 is the same as 1 plus 1, which is 2. And it knows after 2 iterations, if you've kept on for 2 iterations, you're gonna fall out then. So the robot can see that this loop ends. And in fact, that proceeds through all of the single-digit numbers. All the way to 9, the robot can just see from the interfaces that this is happening. And it turns out you have to do 10 as a special case too. because we're going to use 10 in the general case. And because we have to name what base we're working on. So when we get to 10, the robot can still figure it out. We do hit the general case at 11, but the robot can still figure it out because it can see that 11 is 10 times 1, or that 10 times 1 is 10, and so it knows that 11 is 10 plus 1. So still going, doesn't actually fall down until 12. Here, the robot can see that 12 is 10 plus 2, but there is nothing in the interfaces, as far as I can tell, that tells the robot that 12 plus 2 is the same as 11 plus 1. And we're not going to teach the robot math because that would make the robot way too complicated. Math is complicated, even integer math, pretty complicated. We want to keep it simple. So what do we do when we get to this point? We know this loop is going to end, but the robot can't see it. There is some fact that it's missing. We can tell the robot the fact that it's missing by using a static assertion. Here, the static assertion is just something that the robot can assume is true. It can say, okay, if I do all of that addition, I'm going to get 12, because if it wasn't so, no one would be dumb enough to run this program. Don't run your program if the static assertions are failing. So static assert just gives the robot something it can count on, and the compiler checks that, not the robot. But that only goes so far. What about the hard case? What about this one? You can't get out of this with a static assertion. What can we tell the robot that will let it figure out that this loop will end? Because again, we all know this loop's going to end. We can count from a lower number to a higher number. So for this, we have to go a bit into the theory. And I went to my bookshelf, and I looked through a whole bunch of books trying to find the most pithy description of what a loop variant is. And this is what I found. I think this indicates a problem with my bookshelf. Because, man, Bertrand Meyer does get a bit wordy. But here we go. A variant is an integer expression whose value is non-negative after loop initialization and is decreased by at least 1 for every execution of the loop body when the exit condition is not satisfied, but never becomes negative. So it's a thing that counts down, and eventually, if you kept going, you would hit 0 and you would have to stop. So this is Bertrand Meyer. In object-oriented software construction, he's writing about Eiffel, the language he designed back in 70s, 80s. But he's writing this in 1988. I want to point out, this is 35 years ago. We had a language that had a mechanism for expressing loop variants and making sure that loops would end. And nobody, or almost no languages have followed up on that. Not 0, almost none. Mainstream languages, C++, we never even came close to doing that. And I think that it's because there is some problem with this idea. Not that it's mathematically wrong. Actually, it's a little mathematically wrong. We'll get to that. But because this is a hard thing to use and nobody wanted to use it. So let's clean it up a bit so that we can look at what's wrong with it. Here we go. A loop variant is a non-negative integer expression decreased by execution of the loop body. Now, by a non-negative integer, what he really means is a natural number. He doesn't say that. Eiffel doesn't have a natural number type, so he went with none. non-negative integer, making everything more complicated. But mathematically, if you ask a logician, a set theorist, what the right sort of thing to use to ensure a loop or a recursion ending is, the answer is not a natural number. The answer is an ordinal. Ordinals are the right mathematical thing to use to make sure your loop ends. There's a problem with ordinals, though. I am not surprised that Bertrand Meyer did not go for ordinals. So the problem with ordinals is there's too many of them. I would say there's an infinite number of ordinals. There isn't. There are no infinite numbers large enough to count the ordinals. There are a lot of ordinals. So we can't really make an ordinals into an actual type in a real computer language, because actual types in real computer languages have a finite number of values. You can't make a type that has an infinite number of values, which is good, because if you could, it would have an infinite amount of information. It would be very hard to copy. So ordinals aren't working, but by that same token, there's an infinite number of natural numbers. There's an infinite number of non-negative integers. Those don't work either. They just maybe come close enough. But what we really want to do is get away from using a type in our language to represent the loop variant. Really, a loop variant is something that is decreased by execution of the loop body. But we've lost an important property there. There's a mathematical property called well-foundedness that says eventually, if you keep decreasing it, it'll run out. And we've lost that here. So let's put it back in. Ordinals, natural numbers, non-negative integers, you keep decreasing long enough, you get to 0, you can't go any further. It runs out. So a loop variant is something consumed by execution of the loop body in a way that leads to its eventual exhaustion. There's a more general thing to say. I'll clean it up. A loop variant is something consumed by execution of the loop body in a way that leads to its eventual exhaustion. Where have we seen this before? Free energy. Free energy is the cosmological loop variant. Our loops consume it in a way that will lead to its eventual exhaustion. And maybe our loop ends before the free energy is exhausted, we can hope. But if they keep running, eventually, no more free energy. So let's rephrase again. If the iterations of a loop consume some resource in a way that leads to its exhaustion, the loop must end. It's that free energy idea, but we want to bring it closer to home. We want to look at actual, like in our code, and find something in our code that the loop can use up. So this bit of code, we know this one ends. Even our robot agrees this one ends. But what is it using up? Now, Bertrand Meyer and many other people, I shouldn't pick on him too much, but he's fun to pick on, and is this code has a loop variant in it. And Bertrand Meyer would say it's this number that starts out at 12, and it counts down each time, and eventually gets to 0, and then you have to be done by when it gets to 0. But if you're not so hooked on the loop variant is a number, you can ask, 12 what? What are there 12 of in this code that we can use up as we go through the loop? And the answer is there are 12 additions up there. There are 12 times we're adding 1. There are 12 times we're incrementing in this code before the loop. And each time through the loop, we're going to repeat one of those increments. I mean, we're not quite on the nose. Our loop doesn't say, +1, it says ++, but the interface does say +1 in it. And it's going to be adding the same two numbers as up above. And it's going to run through each of these in sequence. And so our robot can know, yeah, we're repeating events that came before the loop, and I'll keep going. And when I reach the loop, we better have figured out how the loop ends. So let's take a different approach here, and we'll say, okay, if the iterations of a loop repeat a sequence of events that happened before the loop must end. You just keep going around, and you tick off previous events off of a list, and that's a finite list, because if it was infinite, you never made it to this loop. So it is a loop variant, but we didn't actually have to count it. We didn't need a variable for it. We expressed it directly by relating one part of our code to another. So let's try using that on the more difficult problem. Here we have our more difficult loop. Where can we get a bunch of events that this loop repeats? The answer is, just take the easy way out. We'll call a function that generates a bunch of events that this loop repeats. Here we have a kind of function, a theorem, I call it, because it says claim implementation in the middle. The implementation doesn't do anything. It just shows how to get from the preconditions to the postconditions. And that's what makes it a theorem. So here, we'll just call this, and this function will give us events to repeat. But to call it, we have to meet its precondition. Why is b less than or equal to e in that precondition? Because it's repeating this branch that we just did. So we're good. We know that we can call this. And our loop repeats a sequence of events in that function's postcondition. So we're repeating a sequence of previous events. Our loop is going to end. That other loop, that one's not our problem. That's somebody else's postcondition. Not our problem yet. And of course, you know where I'm going with this. Now we'll shift scopes and say, what if we're implementing this counting theorem? How do we do that? So I'm going to have to dive into how integers work a little bit. And the thing to know about an integer is that it can be measured with a width that is a number of bits wide, and it may or may not have a sign bit. And those two things tell us everything there is to know about our integer type. I'm going to encapsulate those two things into a class, because I want to use that pair as a template argument a lot. So integer kind just means, is it signed, and what is its width? And I'm going to call out three special kinds, which are the bitless kind, which is no bits, the unsigned bit kind, 1 bit unsigned, signed bit kind, 1 bit signed. And I'm going to use that to invent a class that lets us talk about integers of various widths. And importantly, lets us talk about integers of various widths without constantly hitting the integral promotion rule that drives us back to int. That's really what this is about. I want to talk about little integers without promoting them back to int. And these are going to be the types, where the widening types. The reason they're called that is from last year's talk. But the widening types are the types we're going to use in our proof. So, returning to our problem, how do we prove this? I'm going to take the easy way out again. I'm going to say we're going to convert our parameters to widening, call another version of the counting theorem, an overloaded version of the counting theorem, and that should get us there. It's going to, the loop on the left is going to end because in the interface for the counting theorem, there's another loop that's going to end. Now, I should say I'm skipping the bit here where I show you that the interfaces for int all say int works pretty much the same thing, the same way as widening of the right, signed widening of the right width works. So let's say that stuff is in the interface for int. That stuff is, you can look at the long version of the talk for that. So here we have our, if we compare these two interfaces we have, they look very much alike. And we can say, yeah, this comparison on the right is actually repeated not exactly by the one on the left. I know it looks very much like the one on the left, but they're doing different types. But the one on the left is going to say, yeah, b is less than or equal, the interface for the one on the left is going to say, yeah, b is less than or equal to e, if and only if 2 widening of b is less than or equal to 2 widening of e. That's what I want in that interface that helps us make the connection. And same thing down here. The loop on the left repeats the loop on the right. Again, not directly, but in each of these operations, the interface for the operation does the operation on the right and says something about how it gets the same result. So if the loop on the right exits, the loop on the left will exit, in fact, at the same, after the same number of iterations. And the loop on the right happens first and isn't our problem. It's in somebody else's post condition. Other people's post conditions are not our problem yet. So we'll make it our problem. How do we implement the counting theorem for widening? And for that, let's come back to our integers. I'm going to break integers down into smaller integers in this particular way. That's a convenient place to make the split. And I'm going to do it repeatedly. I'm going to take our integers and break them and split them and split them and split them until we get down to single-bit numbers. And when we get down to a single-bit number, we'll convert it to bool. We'll branch on the bool. And this will, and when we get down there, we'll see that, yeah, our counting will work because we can break our integers down this far. But there's a problem. That's a lot of execution paths. We don't want to subject our robot to a lot of execution paths. That's too many branches, too many joins. The joins are worse than the branches. So how do we get away from showing our robot so many execution paths? We use the power of abstraction. We're going to break this into neighborhoods, and we're going to look at one neighborhood at a time. And each of these individual neighborhoods will only have 3-4 branches. Not very many branches in these neighborhoods. And that way, we can, by considering this one piece at a time, we've turned this problem into a problem that was exponential in the number of bits into a problem that is linear in the number of bits. Power of abstraction. But we get a little extra because there's some repetition there. We only need to actually look at this many. So looking at this many, logarithmic. Went from exponential in the number of bits to logarithmic in the number of bits just by doing abstraction. It makes the robot's job much easier. So we are going to need to know how each integer in this picture relates to the 2 integers that it gets broken into down below. And for that, I'm going to introduce a set of things we can call special interfaces that we're not actually going to build this into our existing operations. I'm going to leave it as something you can call separately because there are branches and not everybody is going to want to know about these branches. So here we go. The reference less or equal axiom here is a special function that we can call. And this one, it's not even a theorem, it's an axiom. It's posit implementation instead of claim implementation. This is something that we can't prove in the language. It's something we're going to assume. And it's basically the rule that says less or equal works right. And so we're going to have a function, reference less or equal, which explains how less or equal is supposed to work. And this axiom says less or equal gives the same answer as reference less or equal. And reference less or equal will just make an inline thing that, oh, before I get to that, I'm going to do this for all the comparisons. And we're going to see all three of these comparisons later on. But reference less or equal is just this inline function that shows us how to figure out if things are equal. I'm going to do it in 4 cases. Less or equal for 0-bit numbers, less or equal for 2 kinds of 1-bit numbers, and less or equal for multi-bit numbers. And those first 3, it's just a table. There's this table that tells us which way the comparison is going to go based on on our numbers and how they converted to bool. And that's pretty easy. That wasn't so hard because there just aren't that many 1-bit numbers. There are even fewer 0-bit numbers. And the last one, what do we do if it's a multi-bit number? Well, we split it. We split our numbers. And you know how this works. We say, well, if the high digits are the same, then we're going to compare the low digits. If the high digits are different, we're going to compare the high digits. And that's how you tell if a 2-digit number is less than or equal to another 2-digit number. So we're just treating these as 2-digit numbers and using that to get lower. And the other comparisons, same thing, the table's just a little different. You could write this. And we do also need to talk about increment. How do we increment various kinds of numbers? So again, reference increment axiom here. And in this case, increment is this awkward in-place operation, so it looks a little different. But here, I'm going to take 2 copies of the same number, reference increment one of them, ordinary increment, actual increment the other one, and say, yeah, you get the same result both ways. What does reference increment look like? Well, again, we're going to break into cases, those same cases. Bitless, unsigned bit, signed bit, multiple bits. And we're going to add one thing up at the top. I'm going to say, no, don't even try to increment the maximum value. We're not even going to bother with that. We're going to stay away from incrementing the maximum value because we don't want to wrap around and we definitely don't want undefined behavior. So caller's responsibility to make sure the maximum value, they're not incrementing the maximum value. So again, the easy cases, there's a table. You can't increment a bitless number at all. If you increment a 1-bit number, you get either 1 or 0, depending on whether it's signed or unsigned, because there was only one value you could increment. And the last one, you know this, I'm pretty sure you know this. When you have a multi-digit number, a 2-digit number, you ask, is the low digit equal to its maximum value? If it's not equal, you increment the low digit. If it is equal, then you increment the high digit, set the low digit down to its minimum value. That's it. We're just explaining how increment works in terms of increment for smaller types. And when we get down to the bottom, in terms of converting the bit to Boolean. So that's all we need for preliminaries. Let's return to our proof. What are we going to do? We're going to break into cases. Those same cases all over again. Bitless, unsigned bit, signed bit, and multi-bit. Let's take the bitless one first. It's going to be pretty easy. Here, if we have our bitless one, we're going to say, let's call the reference not equal axiom on our bitless numbers. And that makes the robot walk through this table. Except by the power of if const expr, the robot doesn't see all the table. It only sees the part that matches this case because there was an if const expr around it. So this tells the robot that not equal is always going to return false. And I'm going to copy that over here. That's for our benefit, not for the robots. I'm going to put that over here and say, yeah, when we do that comparison, it's going to return false. So how does this relate to the post condition of our theorem? I'm going to bring that around to the other side here. I'm going to say, oh, when we do our post condition, we're matching the comparison that happened in the implementation, because that's how you achieve post conditions. You match something that happened in the implementation. And here we compared these two things. We know, oh, first time we compared it, it was false. We repeated that comparison, it's still going to be false. We know that false makes the loop end. Okay, so that's the easy case. The unsigned bit, it's going to be a little harder. I left some room. But what we're going to do is we're going to concentrate on the hard one, which is when AB is not equal to CD. When they're equal, it's going to be pretty easy. But when it's not equal, we're going to actually increment something in there. We're going to start by calling the less or equal axiom. And so our robot walks through this table. But remember our precondition said less than or equal return true. So we know we're not in the upper right corner of the table. And we'll put something down below to record that for our benefit. Then we'll call the reference not equal axiom. But again, this one we know has to return true because we wouldn't have reached this point if not equal returned false. It would have gone the other way at the outer branch. Yes, we already know we're not in the upper right corner because these tables match. But now we know we're also not in two other corners. We know we're in the lower left. We know that we are in the case where AB is 0 and CD is 1. And if we call the reference less axiom, we know, once again, the tables all line up with each other. We know we're in the lower left corner. So we can see that AB is going to be less than CD because AB is 0 and CD is 1. Finally, we're going to talk about how to increment this reference increment axiom. And this says, yeah, if we increment this, we're going to get 1 because that's what the reference axiom said we get when we increment an unsigned bit. And we can do it because we know that AB is 0, not 1. It's not the maximum value. So there's the implementation of our proof. That's all we need to know. We just have to match it up with with our post condition. And our post condition matches various lines in this. The first time we come to the loop condition, it matches the if statement, the condition in the if statement. Then we come down to AB less than CD, we come down to XY less than CD, and it matches AB less than CD. There's the same values there. And when we do the increment, it matches the increment that's in our proof. And when we come to the next loop condition, it matches this claim at the bottom that says, oh, that not equal, it's going to return false. The loop exits. So just matching things in our implementation is how we show that our post condition holds. Signed bits, very similar. Little different, but very similar. We bring in all those tables. We know that we're in the upper right corner. And when we compare it to the loop in our post condition, it matches up in pretty much the same way. So now the hard one. multi-bit numbers. How do we show that we can count from AB to CD? Well, first thing we're going to do is split it into high digit and low digit. And then we're going to generate a whole lot of intermediate pairs of digits. You've seen this before. You know how to count. How do you count? Well, going down the column, you increment the second digit until it reaches its maximum value, except for that last column where you increment it until it reaches D, where we'll stop. What are we doing in between columns? We increment the high digit and set the low digit back to its minimum value. That's how we count with two-digit numbers. And we can collect all that code together and say, yeah, this collection of loops produces the right number of pairs of digits. It goes on for the right length of time. But now we have three problems. Why do these loops end? What can we do to show the robot that these three loops end? Well, I'm going to use the same trick. I'm going to call the counting theorem. But not recursively, I'm going to call a different instantiation of the counting theorem for smaller numbers. And eventually, of course, that will bottom out on the one-bit numbers. So I'm going to call the counting theorem. And yeah, our loop here just matches what happened in the postcondition of the counting theorem. So this is great, except we didn't actually show that the precondition holds. How do we know that x is less than or equal to c? Now, let's go back to the beginning of this. We'll stick in a call to the reference less axiom. Say, well, yeah, there's really two cases here. One case is that a is not equal to c, in which case we know a is less than or c, and x at this point is equal to a, so it's less than or equal in that case. If a is equal to, if a is not equal to c, sorry, that's if a is not equal to c. If a is equal to c, then of course we know just from our helpful interface that if they're equal, it's definitely going to be less than or equal. So two cases, in both cases we know that that the things where past x is going to be less than c, going on to that side, different name, but AB is going to be less than equal to CD. So that's our first loop. What about the second one? I'm going to call the counting theorem again. And again, our loop matches up perfectly. Our only question is, how did we get the precondition? But yeah, I'm going to say a helpful thing for less or equal to tell us is that you're always less or equal to your maximum value. So that precondition just falls out of things we'll write into the interfaces. Last one. Counting theorem again from y to d. It matches up again, just perfectly. But why is the precondition holding? Well, because remember there was those two cases? If a was equal to c, then we already knew that, then we went right through the loop. We didn't actually do the upper loop. And we do know that b is less than or equal to d, so we're good. Otherwise, we went through that loop, and y is equal to its minimum value, because that loop always exits with y equal to its minimum value. And if you do an iteration of it. So either way, we know, because d's minimum value is y's minimum value, we know that this precondition is going to be met. So there we go. This code now explains its loops, but what it doesn't do is give us the events that match our postcondition. It's doing this two-digit counting thing, which runs on for the right amount of time, but it doesn't match this combined counting. So what do we do? going to do a little refactoring. I'm going to pull out these bits where we increment things. I'm going to put them into these little named lambda functions. This is a very helpful refactoring tool. And of course, once we do that, we use the names instead of doing it. And the other thing that you really should do if you're using this refactoring trick, add assertions that say you're using it in the right place. We are going to increment the low digit when the low digit is not equal to its maximum value. We're going to increment the high digit and set the low digit to its minimum value when the low digit was at its maximum value. A little more refactoring, these comparisons that tell us if we're at the end of a column. Going to give it a name, going to use the name. And again, you compare against max when x is not equal to c, you compare against d when x is equal to c. Just a little refactoring. But now we'll take advantage of the refactoring. Let's come back to the beginning and introduce a new variable, xy, which starts at ab. It's x and y put together. And we're going to keep it in sync with x and y. Xy will always be x and y put together. And here, we'll put into here, whenever we increment either x or y, we're going to increment xy, and we're going to call the reference increment axiom to explain to the robot why xy is still x and y put together. And that's just because we're repeating the thing that happened in the reference increment function. We're also going to, in each of these comparisons, make a prediction about whether xy is not equal to cd. On the left-hand side, when x is not equal to c, we're going to predict xy definitely not equal to cd, because x is not equal to c. On the right-hand side, when x is equal to c, we're going to say, yeah, it's the same as comparing y to d. So we make our predictions, and if we come back here, our postconditions are matching the things that we put into that refactoring. So each comparison in the loop condition is either going to match the comparison on xy that happened in not max or not d, whichever comes next. Each increment is going to match the increment in advance y or advance x, whichever comes next. The loop in our postconditions is repeating a sequence of events that happened in our implementation. So if we know the implementation ended, so this loop also ends. That's how we achieve our postcondition. It matches the implementation. Now, we didn't actually talk about this other claim, xy less than cd, which is sort of a bonus thing to stick in there. I'm going to put some reasons why xy is going to be less than cd over here, because x is less than cd when it's not equal, and because y is less than d in the bottom loop. Once again, factor them out. Add an assertion saying we're using this in the right situation. Use the reference axiom to make a prediction about what xy less than cd will be. And in this case, it'll be the same as what we're returning. So once we've done all that, we come back, and even that line always matches stuff that we did in our implementation. So our postcondition holds because because it does the same branches that happened in our implementation, and we made it through and the claims held. So there we go. We can count. And I want to point out that if we can count, we can do any of Bertrand-Meyer's numeric loop variants. They're easy at this point, but we're a little more flexible now. We just do it by repetition. So the next time you're faced with this question, if you write your code carefully, and if you have good interfaces, which, someday we'll have syntax for it, it'll have an answer. It's because the loop ends because it repeats a sequence of local events that happened before the loop started. Each iteration consumes some of those events, and the events before the loop, because there are finitely many, are eventually exhausted. And that is a nice local reason, and it's something that our robot ought to be able to follow pretty well because it was checking for repetition anyway. And I'm hoping for one more thing. I am hoping that it's a practical way to express why a loop ends, because I don't want to go another 35 years without expressing in our programs why our loops are going to end. Thank you for listening. Are there any questions? We have very little time for questions. Okay, a question about interfaces. Okay, the question is, I used extend stability in places where I was passing things by const value. And the question is, was it the caller's responsibility or the implementation's responsibility to maintain that value? And the interface is the one that says, if it says if I said extend stability, I'm putting it on the caller. And I think that's the right answer for things passed by const value. So it's, yes, it is a bit of a convention of mine, but the ground truth is, what does the interface say? Not something that you infer from the function signature. So we are over, so I will be around in the hall, or I'll be demiking a bit here, but thank you.